This conference will now be recorded.
So sorry, I was speaking on mute. Yeah, let's go ahead and get started with our today's discussion. So today, I would like to start with Hadoop history. Then later on, I will be taking to the new concepts today. So let's go ahead and see really how Hadoop was born, which means like if you take any programming language, the history always will start with probably one person, probably a small garage, where they'll be working with a small number of uh, people. Then later point of time, they're going to extend that one to the market, and that's how the programming language is going to capture most of the times. The same thing has happened with Hadoop also. Let's see. I mean, sometimes one of the interview questions also might be asked out of this one. Let's go ahead and understand really how Hadoop was born in this market. So back in 2002, okay, called two guys, uh, Doug Cutting and Mike Caffarella. So these two guys started working as a part-time. So they are already a part of Yahoo, and they started working on one product. The product name is called Nudge product, and they started working as a part-time. Okay, so as a part-time. So this Nudge product is a open source search engine. Okay, it's not a like commercial one like how you had Google and all, Yahoo and all. They don't want to build that one. They would like to have an open source one, open source search engine. So when you say Google and all, like when you want to customize as per your changes, there is no way you can change using this one, right? So that is the reason they wanted to make one open source so that anyone can use their system to change as per their requirement actually. So in 2004, right? So they made their first cut ready, and the first cut was ready and completed 20 node cluster kind of thing. Okay, so they were good with the not exactly the same concept that we discussed so far, but here and there they were able to put the computers together and they were able to see that 20 machines were working fine and tried to extend to 40 node. So they were trying to extend to the 40 node, but it was not up to the mark. So which means it was not working at all. So they tried to do that 40 and it was not working. So they thought like, yes, 20 node, no, who is going to use in this world, because the data is like with 20 node, there is no way we can maintain this lot of data, such data. That is the reason they thought like 40 node is not working. They thought they can stop working on this one actually. Okay, there was no progress also for some time. So back in 2005, right? So what happened? Google released a white paper actually. So Google is the one who has already facing some issues with the data, and they released a white paper. In that white paper, right, they clearly mentioned very clearly Google file system. So which means how huge volume of data can be handled using this GFS actually, right? In short, we'll be calling as a GFS. And also they describe very clearly Google Map Reduce, right? So how to process this data also they described very clearly in their white paper actually. So luckily these guys have seen that one. They thought, hey, why can't we apply these concepts towards our 40 node cluster? So they started working again on top of that product and they started seeing some progress, right? They started seeing something kind of 40 node is going to work for them. So now in 2006, Yahoo is the one who was already facing some issues with the data, which means they're already having a lot of uh, data in their warehouse, and to just make sure the data is available for their end users, they are right, they are trying to analyze the data, but they are already facing some issues with the existing one. So they approached, right, Yahoo has approached these people and they said, hey, you people are working as a part-time, you don't have to work as a part-time on top of this one, you can just go ahead and work as a full-time on top of this one, plus we are going to provide the infrastructure and also team for you. Around 20 members team they have provided for them actually. So now that's how they started working towards, or that's how Yahoo became the primary contributor. But here one condition from Yahoo side here is, so they have to start working towards the big data. It's not something a nudge product they are working open source one, because it's already there in them. They don't want to just have the open source one, they wanted to have this open source big data related things. That's how Yahoo became primary contributor and uh, started working towards big data, friends. Okay, so that's how big data came into the picture. I mean, they started working, they agreed for that, and they started working. So slowly they started extending the 20 node, 30 node, 40 node. So they extended, it is working excellent actually. In 2001 8, they implemented, right, 4,000 node cluster, right, 4,000 node cluster in Yahoo production itself, right? So where it was dealing with end users directly. So that's how the journey has started, and it is continuing. After 2008, they started introducing the new echo components um, based on our different problem statements that you have. They try to implement the one by one. That's how this big Hive, HBase, and all this were born after this one actually. Okay, so that is what the complete history about the Hadoop actually. So you see very clearly they started working with the Nudge product, and it is ended up with the big data. So definitely the product name is should not be that one actually, right? The product name should not be that one. They wanted to have their, they wanted to have a different name actually. So that's how they started working. I mean, they started thinking about naming the different name for this one. So initially they thought the different names for this one. So everyone started discussing within a team, but no one is like agreed with that names actually. That's how they started thinking to name this product name. So one day what happened, duck cutting was, right? He was watching when his kid was playing with his toy actually. The tiny yellow color elephant toy he was playing. The his kid is the one who has like named his toy name as a Hadoop actually. So all of a sudden he thought, yes, so why can't I give my product logo as elephant, because this is also huge in size. My product also is working with big data actually. So that's how he started thinking, and he thought he can give this logo as well as the name, that whatever he named that Hadoop name, he thought he can give this product name also, because it's easy to remember, easy to write, easy to spell, and the other thing is there is nowhere in the copyrighted issues from the website actually. So that's how he has introduced in the team, and everyone was very happy with that name, with that logo. That's how the product name and logo came into the picture for this one. There is no meaning of Hadoop and nothing. So just it's a his kid toy name. That's how he named as a Hadoop. That's how they named this product name as a Hadoop. Okay. So that is what the complete history about the Hadoop actually. Okay. So you don't have to take the notes. I will save this one and I can share with you, don't worry. Okay, so we will continue appending the data to this one by one as we proceed further. So we'll see. Okay, so you don't have to take the notes. Hadoop history. Okay, so now let's see. And so far we discussed in our yesterday's class the pseudo distribution mode, how it is going to work and all. So let me just extend a few more concepts. So we did discuss yesterday about like no hiccups, which means you are thinking your cluster is working always um, good for you. There are no hiccups at all, which means everything is like on time and it is working for you without any issues actually, right? So no system down and everything. But always, as you see here, two things. One is these are the commodity hardware, cheap hardwares, general purpose hardwares, right? They may go down any given period of time. That is the one thing. The other thing, even though you are using enterprise hardware, when you see, right, multiple machines, multiple guys are involved in your system, obviously you may expect the hiccups because, right, they may go down any given period of time actually. So you have to tolerate them actually. So you have to make sure, right? You have to make sure they are like, even though they are going down, what are the tolerance thing levels or tolerance concepts that we are going to have it actually. That's what we have to discuss today actually. So let's see, whenever your name node is going down, we have a backup for to recover the metadata. But still, whenever the name node is going down, right, how your cluster related things will be continued, we'll be discussing in our further discussion. That one we are going to discuss down the line. So master computer related things, right, name node, second name node, job tracker, if they are going down, how the operations will be continued within your cluster, how your task will be continued within the cluster, we will see that one in a advanced one. In 1.x, very straightforward. If master computer is going down, definitely you have to bring one other machine back and make sure you have to install all these things, configure related to that master computer and start the daemon there, and till that point of time your cluster will become the inaccessible. That is what one of the biggest disadvantage in our Hadoop 1.x, right? Because if the name node is going down, until you bring another machine up, there is no way you can process anything. So if you see the job tracker is going down, until you bring the other machines, there is no way you can see your processing will continue actually. So that is where you see very clearly master computer, whenever it is going down, you have to have some downtime actually in 1.x. But of course in 2.x 2 version, we have very well addressed that you don't have to wait all the way. There are some standalone standby nodes will be there to address that one. We'll come back to that. And coming to the data nodes downtime, which means like whenever they are going down, right, definitely they will go down because they are commodity hardware and also multiple guys are involved, 200, 2000, 20,000. So out of that, if they are going down, how we are going to tolerate it, right? That's what we have to understand very clearly actually. Okay, 1 minute. I'm so sorry, one of our participant is waiting for this one. So, I mean, whenever you see your link is not working, please check your email. So every 15 days, this one will be changing actually. Okay, so okay, sorry about that. Okay, so now, yeah, so whenever these machines are going down, let's go ahead and see how we are going to tolerate that one. So now let's see. initially, like let's go ahead and see temp.txt file, who is having 100 MB, and B1 is having 64 MB, B2 is having 36 MB. So that's how we manage the data, and B1 is here, and B2 is somewhere else here actually. Okay, so that's how we just distributed our data. And also let me add one more guy here. Okay, so this is data node 5. Just think that way. Okay, data node 5, and I'm going to see task tracker and node manager. Okay, so now you see these 5 data nodes that we have. We distributed your data into the data node 1 and data node 3. So now you see, anytime whenever you want to process the data, the request will go to the job tracker. You know that. Anytime you want to retrieve the data, your name node will come into the picture out of your data nodes. Whenever you wanted to store the data, your name node only. But whenever you wanted to process anything, the request will send to the job tracker. So indirectly you came up with the map reduce or any hive script or pick scripts that came, and it is being just sent to the job tracker or resource manager. Now resource manager or job tracker will be in touch with your name node. Name node is the one who is going to scan, because the reading is happening, right? So he wanted to read the data where it is being distributed in our cluster. So that's what the request has been sent to the name node. Name node is the one who is like having this one actually. So now you see B1, I mean here you see B1 is here and B2 is here. That's how your metadata also is being settled here actually. We know that. So now here, let's go ahead and see, right? In a fault way, right? You see this data node 1 went down because of some issues, because of the network issue, because of the system issue, it went down, right? So now what is going to happen? If it went down, what is that? Whenever your job tracker is sending any request to the name node, so you know that this machine went down. Now you see only the portion of the data is available. Then do you think like you will continue running processing this one only against B2, and you're going to say that, hey, B1 is only small portion of the data, I'm okay to skip it? Okay, that is not how the system is going to work out here. So 100% data has to be available before you start processing, even though against 1 terabyte of data or 1 petabyte of data also. For example, one block is not available out of your whole data. For example, one of the node went down, then your processing will not be continued until unless you recover that one actually. Same thing here, 100% data should be available before you start processing actually. There is no percentile of data available at all actually. Okay, so you have to understand very clearly. So now you see very clearly this is down, then only the B2 is available. So I need to recover this one. So at the time of processing only I need to recover this one. At the time of processing only I need to recover this one. So the answer is, right? The answer is obviously no. If you are processing at the time of recovering, then right, there is no way you can see your tolerance way actually. So for that reason only, right, what we do here is at the time of copying your data into the Hadoop cluster, what Hadoop is going to say that, hey, please go ahead and make the 3 copies actually, right? 3 copies. So the first, let's go ahead and have B1 comma B1 comma B1, then B2 B2 comma B2 actually. So these are the, right, 3 copies are made for us actually. So B1 here and one more B1, for example, they just copied here, and one more B1 is copied here. and one more B2 copied here, and one more B2 copied probably here. So you see 3 copies are available at the time of, I mean by default, I mean this will be again configurable actually. By default I'm talking about. So in Hadoop 1.x, in 2.x, Hadoop has recommended for you to just make the 3 copies. B1 here, B1 here, and B1 here. B2 here, B2 here, and B2 here. So few facts about this one here is, I mean, before I move on this one, this concept is called replication factor, replicas, which means you're maintaining the copies of your data actually, right? If you observe very clearly, you are not exactly maintaining the data node copy, that complete your machine image you are not making, but the data that is there is maintained the copies in our, wherever it is possible, it is maintained actually. So this is called replication factor actually. So replications, right? Replication factor. So the default replication factor is 3 in Hadoop 1.x, 2.x, and it can be configurable, which means minimum RF you can have is 1 and maximum RF anything. Okay, so this is what the just configuration that you can have. We will see very clearly how we can configure this. So now here you see, so these copies, it's not something you are prioritizing, friends. It's not something this is what highest priority. If this is not available, then only I need to go ahead and search for this one. If this is not available, then only I need to search for the third copy. No. So indirectly, all are going to have the equal priority, right? There is no such rule like first one is one highest, second one is highest, third one is no such concept. Everyone is having all equal priority, but based on 3 copies, whichever is having the more bandwidth, whichever is having the less workload, those will be picked by the framework actually. So we'll see down the line how that can be categorized here. So you see B1 here, B1 here, and B1 here. So out of this one, we know that data node 1 is went down, so 1 copy is not available. So I see only 2 copies, right? B1 here and B1 here actually. So out of these two B1s, right? So which one will be picked? So we have to understand here very carefully. Okay, so B1 is here, B1 is here actually. So out of these 2 copies, anything can be picked actually. Anything can be picked, either dead node 2 or dead node 3. Okay, so data node 2, for example, you decided to, or your framework has decided to pick the data node 2 actually. So you see very clearly data node 2 is been picked. Okay, data node is 2 is been picked. So now you see you are able to send the request to this one. So now, right? So now the same thing for your B2, you have copy 1, copy 2, and copy 3. Okay, so you see out of this one, whichever is having the more bandwidth, like I said, for example, dead node 5 is having the more bandwidth. Now dead node 5 will be read out of this one actually. Clear? One minute, I'm so sorry, 1 minute. Sorry about that. Okay. So now you see B2 has been picked from the dead node 5 actually. So B1 from the dead node 2 and B2 from the dead node 5. So that's how your processing will be continued actually. So you see very clearly, even though your dead node 1 went down, you are able to make sure your data is available all the time to process the data. You increased your data availability in your Hadoop cluster with this replication factor. So this is called fault tolerance. You are able to tolerate your fault with this replication factor. So you may ask now, hey Shiva, instead of copying 100 MB of data, literally you copied 3 copies, which means 300 MB of data, 1 TB, 3 TB of data. So do you think like still your cluster can tolerate that? Yes. So of course you can do the horizontal scalability. So how many nodes that you want, you can simply just go ahead and add to that one. There is no problem at all adding the more nodes to that one. That's what our Hadoop itself is going to uh, accept that one. So definitely it's not a issue for us actually. Okay, so this is called replication factor. So any questions on this one?
Shiva,
Yeah.
regarding this nodes, I mean, initially when we talk about the naming node, okay, name node, the master node.
Uh-huh.
So when it comes to the how many number of node cluster, so it is like 6 node cluster, right? Now it will be like 8 node cluster.
Exactly. So whenever someone is asking how many nodes that you have to count all the nodes, including your master nodes also.
These 3 nodes.
Yes, all nodes. It's not
Okay, okay,
master and slaves, all nodes, computers. Nodes is nothing but your computers, machines.
okay. And these replicas, I mean, will it get vanished after the process, or still it will exist?
No, at the time of copying your file itself, it is there. No matter where you are processing or not, it will be it remains the same thing actually. It's not something at the time of processing only or replicating. At the time of copying the data, right? Which means now today I'm just copying. I just made 3 copies. If I'm not processing today or tomorrow or for 1 month, does not matter. You wanted to maintain the 3 copies, they are going to be there 3 copies actually.
Okay, fine.
Okay. So now let's see. You see very clearly data node went down, right? Because of some issues. Now you see, right, how your name node is going to know that your data node went down, how your name node is going to know that your cluster, I mean you should not send any request to the data nodes actually. So for that reason only, right, so how your name node is going to assign the work to the data nodes, how your name node is going to know that whether these guys are not available, and also how your name node is going to know that how the bandwidth is available, how much bandwidth is available, how much more data it can accept. All these things we have to know mechanism actually. So for that reason only, each and every data node, right, each and every data node every 3 seconds is going to send the signal kind of thing back to the name node. Every 3 seconds a ping, simply a ping. From, if you know a little bit about Unix, it's a ping. Every 3 seconds they are going to send it. So we'll be calling this one as a heartbeat pulse signal. Any name that you want you can have actually. So what they are going to do here is first 3 seconds, for example, let's go ahead and take the first data node, one example. So first 3 seconds your name node did not receive the signal from the data node 1. Then it will wait for the second attempt. That time also he did not receive. Third attempts, that time also he did not receive. Then he's going to confirm, yes, this guy is a dead guy, even though after third attempts also I did not see any signal from the data node actually. Then immediately he is going to decide this guy is a dead guy, which means he's no more active. He cannot accept any work from my end, so I cannot send any work to him. That is the first thing. The second thing, yes, I need to start recovering the data that is there in this node actually. So now he knows what data is being shared to this guy. He knows that with the help of your metadata actually. So now your name node is going to look the metadata and is going to see that something like that B1 that is there from the temp.txt file. The same thing from different files, you're going to see the different blocks here. For example, 2000 blocks from the different files. For example, 100 files, 2000 blocks were there. So those 2000 blocks has to be recovered somewhere else actually. So now that's how your name node is going to look the bandwidth in other data nodes, because with this one he knows that whoever is working, who is having how much bandwidth. So now that's how, right, that's how these blocks whichever were there here, those will be started recovering actually. So here B1 for this one here and here. So your name node is going to send a request to data node 2 or data node 3 just to copy this guy, right, into any one of the node wherever it is having the bandwidth actually, right? So let's say B1, you copied B1 to B1 here actually. Okay, so now what happened? You maintained copy one, copy one, and copy one. 3 copies you maintained here actually. So within 9 seconds itself, you are able to maintain the 3 copies actually. So now this guy is dead guy. So no more it is active, and no one is going to send any request for this. The same thing how the B1 is being recovered. The same thing other files blocks also will be recovered the same way actually. Okay, that is how the recovery is going to happen in our Hadoop cluster. So there is a fault from his side and he is able to rectify himself. He is able to heal himself. It means you don't have to, you as an admin, you don't have to recover manually. This is automatic process actually. Okay. So any questions on this one? Okay. So along with this heartbeat, we are
Hi,
going
Shiva.
to,
Yeah,
yeah,
like in case if we just repair the system B1, so like it's gonna bring all the data back, or like can we add
good.
a new node here and like it's gonna shift all the data to the another one?
Excellent question, that one. Yeah. So let's address that. So now, before that, I thought I can address after this one, but let me just complete this 2 minutes of topic, then I'll come back to that. Okay. So now you see, along with this heartbeat, we are going to send, or data nodes are the one who is going to send block report friends, which means every 3 seconds, along with your heartbeat, we are going to send the BR block report, which means how many blocks are there from this file. Those blocks are belongs to what file? How much overall space is left over out of this one? How many more blocks it can accept, right? So whether the data that is there in the blocks are good data or it's been junk data has been sitting there actually. So all these things are going to be sending from the data node to the name node. So simply your data nodes also are going to maintain the data net level metadata. Your name node metadata is going to be the global way. Your data node metadata is going to be the data node level. So which means these blocks belongs to what file, how they are looking, right? And how much is the leftover is there, what is the total capacity, how much is been occupied, how much is the leftover is there, how much work you can accept. All these things will be there in the metadata indirectly. This all metadata, based on this all metadata only, your name node is going to shuffle your main metadata and is going to keep up to date. Because if this guy is going down, right, earlier you had B1 here with the data node 1, your name node should not route the request to the data node 1 even though it went down. So how you're going to know that your name node is going to reshuffle, or your name node is going to correct it, your data node went down, there is no way I should not send that based on the your metadata. Actually your metadata will be reshuffled how, based on your block report. Every data node is going to send that information back to the name node. Based on that based on that only your name node is going to make its metadata up to date actually. So immediately it's going to correct it, and going forward this no more related for your block one is no more related for your data node one. It is gone, the connection itself is gone, or which means there is no way it can go ahead and just send the request to that false request to the data node 1, where your data node 1 B1 is not there actually. Okay, so that is what block report and data node metadata. I will show you data node metadata, name node metadata, all these things in our hands-on. The next thing is, yeah, so we were able to see, right? We are able to see very clearly this guy went down and somehow we recovered as per our Syed's question. So you see, somehow the admin guy came into the picture and fixed it actually. There was a network issue and he fixed it and he's ready to join actually. So now few facts about this one is you don't have to bring other machines to join this thing actually. Automatically you can join. That is what beauty of your Hadoop. So in order to rejoin your fixed systems or failure system, you don't have to bring the other machines, other system down to add it. Automatically you can add it. That is what the rule number 1. The rule number 2 here is, you see, when you fix it, it came back to Hadoop. It does not mean that, right? It does not mean that you are going to, right? It does not mean that you are going to retain this data here, whatever it was there. Instead, you are going to wipe out, which means, so everything you're going to clean. So indirectly format, you're going to format this data actually. So once you format this data, right, it will become the, I mean, once you format this node, it will become free actually. It is empty. So now here, again, you're not going to attempt, or your name node is not going to attempt to recopy or retain the old status of the data node 1 by copying the B1 or from other files data into this one to retain the old status. No, you are not going to, or your system is not going to do that one, because you settled already the data. Then why you have to again go ahead and pull the data and mess that existing things actually? When you settle, you know that based on the bandwidth only you settle the data. So that is the reason you are not going to just disturb the existing one or settled process. It will be as it is. So this node is going to accept the more work, future work, right? Which is now whatever it is like coming from name node, those things will be addressed actually. Those things will be taken the high priority for this node actually. Okay. So that's how we are going to do. Sayed, did I answer your question?
Yes, Shiva, thank you so much.
Okay.
Hi Shiva, Himanshu here.
Yeah, Himanshu, go ahead.
So Shiva, like in SQL Server, if we have some table and it has got like around 10,000 records, so when we
Mhm.
say that temp.txt is 100 MB and it is divided into 64 and 36 MB parts, right? So does that mean that that particular table will be distributed among three computers, or how is it like?
Exactly. Exactly. You are, the 10,000 records might have divided into the three things and it might have distributed into the three computers actually.
Okay. So, Shiva, if I mean, if that table has sales data and we need to calculate the total sales, something like that. So, at a given point of time, that our program will be executing on three machines, right?
Exactly. So
Okay.
wherever your data is there, those machines will be involved in the processing. The processing we'll see at the time of map reduce discussion. We are just discussing
Okay.
about the
Okay.
storage things
Okay.
actually. So
Okay.
processing in depth, definitely we will discuss that time actually.
Sure.
Yes.
Okay. Sure. Thanks.
Okay. 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 So that's what the majority of our discussion has happened. Let's go ahead and just see one more thing, then we can move on with the hands-on. Okay. The next thing is, let's go ahead and see. I mean, um, let's go ahead and see our capacities actually, which means if someone is asking what is the maximum data that you can store in your HDFS file system in your cluster. So how many nodes are there? That is different capacity. How much data that you can load? What is the total capacity that your cluster can handle. That's what you have to understand actually. So this is purely admin concept, but like I said, we are going to cover a few of the admin important concepts where developers should understand. So that's how this concept is here. So let's go ahead and see. So here you see very clearly each and every mission, around 4 missions are here and 3 master missions are here. So you know by this time, whenever you say storage, right, your master computers will not come into the picture to store the data. Only the right data nodes will come into the picture. So let's see, right? So let me just have 500 GB hard drive that you have, right? And 32 GB RAM that you have. So now definitely RAM will not come into the picture because at the time of processing, let's go ahead and discuss the RAM thing. So now 500 GB is the hard drive that we have each and every machine. So initially we are going to discuss about the same configuration across your all machines, which means homogeneous configuration, which they are going to follow the every machine, every node is going to follow the same configuration. So hey Shiva, is it mandatory? No, Hadoop is not going to mandate you. If you want, you can have a homogeneous. If you want, you can have a different configuration, heterogeneous actually. So we are going to discuss the two options actually, right? So we'll see first 500 GB is the hard drive each and every machine is having actually. So now 500 GB is each and every machine is having. So then if I'm asking you what is the total configured capacity or what is the total data that you can hold this in this Hadoop cluster, we cannot say that 500 into 1 plus 2 plus 3 plus 4 then 2000. I cannot just go ahead and have the 2000 GB is the total data that I can store actually. I mean, a layman guy, a guy who does not know much about Hadoop backgrounds, they can calculate that, but that is not how we can do it actually. So these leftover one, like something you know that OS will be taking something and your Hadoop framework also is going to take some space. Everything after it went all, this 500 GB is the leftover one, right? So after everything went, the 500 GB is the remaining space is available out of your data nodes. Okay, so now out of this one, let's see how it is going to happen. Okay, let's see 500 hard drive here. So now, so one thing that you have to understand, each and every machine is going to contribute towards your HDFS file system, friends, indirectly. So I am going to build a common space kind of thing. So I mean, to view at a high level how much space is available on the this thing I'm calculating here. At the time of storing, again, I'm not going to put these all machines together to build the bigger system, friends. Don't get confused here. Simply to calculate the capacity, I'm just putting the all these spaces, piece spaces together to see, yes, this is the whole data that I have. So for example, if we are having a team, within a team, if you have probably distributed some money or amount or any work individually, right, you know that how much each team member is having money. For example, if you want to know your team is having how much money, you're going to just consider individual money and you're going to sum them together. You're going to say that yes, my team is having this much money or this much workload I can accept individually. Each and every team member, how he can accept, how much work he can accept, that's what you're going to put together to see the final team strength actually. Exactly here also it's going to happen, but individually when you are going to assign any work, you know that at the individual level only you're going to accept. It's not something all together you can do it actually. Similar way, I'm going to build this space right out of this each and every machine actually. So this is called HDFS pool, right? HDFS pool, HDFS pool, or we are going to say that, and DFS pool or block pool also we say. So all are the names actually. So HDFS pool capacity is nothing but so how much is being like space is available out of your DFS actually. So now here it's not something that 500 GB I can contribute to this one actually. So instead, so my Hadoop is going to say that yes, these were just think like these complete spaces of 500 GB. So out of that, we are going to divide that space, right, vertically into two layers actually. So indirectly your machines, your hard drive, whatever you are using in your computer, we are creating two layers out of that actually. That hard drive, whatever it is there, the moment you install the framework, the hard drive is being divided into the two layers. The first layer you can call it as a DFS, a distributed file system, DFS indirectly you can call, and the second one is for non-DFS, local. Non-DFS, local, both are same. So most of the time we are going to call it as a non-DFS or local also we can say. So what is this actually? So I'll come back to this one. What is the purpose of non-DFS? But each and every node is going to do the exactly the same thing. This is going to be the non-DFS, right? This is going to be the local, non-DFS, local, non-DFS, local. Okay, so this is what your DFS, I mean DFS, non-DFS, and okay. So this is how you just divide your space into the two layers. So indirectly, you have two file systems indirectly. We'll come back to this one, how we are going to utilize this one, how we can locate each and every machine, these two spaces. I'll take you very clearly in our hands-on experience actually. So now here you see, for example, out of your 500, I'm just calculating, right? There is a rule where you can configure how much percentage you can give for the DFS, how much percentage you can give for the non-DFS. For example, this I have given 400 here and 100 here out of your leftover. Then 400 here, 100 here, 400 here, 100 here, 400 here, 100 here. So that's how we just created this one actually. You see very clearly this guy 400, this guy 400, this guy 400, this guy 400. So that is what your DFS HDFS pool actually. Okay, so it's a contribution of your each and every data nodes together. So what is the DFS capacity, right? So 4 into 400, it's going to be the 1600 GP. So now you can calculate, right? You know that how to calculate this DFS capacity out of your cluster. If you are asked to do that one, you can very well do that. Non-DFS capacity, right? So 4 star 100, it's going to be the 400 GP, right? And total capacity we'll be calling as a configured capacity, friends. So configured capacity for, I mean, so indirectly sum of your DFS and non-DFS equal to 2000 GP. So which includes your DFS and non-DFS. Okay, so these are the numbers are very, very important. So now here you see what is the purpose of your DFS. The DFS, as you know, so far whatever we discussed, your block division, your replication factor, and the recovery management, all these things are going to be applicable for this space actually, right? Indirectly, whenever you say that my data node is accommodating the block one out of my temp.txt file, the data will be here only, right? The data will be here. So whenever you say when this data node went down, the recovery is going to happen only this portion actually, right? So this is what this one, the blocks, the replication factor and everything you are going to see out of this portion only. Okay, friends. So now we are clear. Whatever the concepts that we are discussing, whatever the data node one has to or data nodes has to do for you, this portion of the things only are going to happen. This file system is only going to do for you. Then non-DFS. What is the purpose of non-DFS? Non-DFS, don't get confused too much. It's your local file system. So today, how you use your Windows file system, that is what your non-DFS, or Unix file system, that is what your non-DFS actually. When you store any file in this space, do you think like your data will be divided into the pieces? No. If you, for example, you lost your computer with the hard drive, do you think like this will be automatically recovered in your system somewhere else? No, there is no such concept. So that file system is a normal one, as you see in our kind of a legacy one actually. So now, why we had, right, this portion of the non-DFS also out of each and every data node, right? You know that DFS is there, that is well and good. We know that what is the purpose of DFS, but what is the purpose of non-DFS? So the main purpose of your non-DFS is, right, at the time of execution, at the time of map reduce execution, when you are processing these blocks, right, your MR basically, it's a combination of stages, friends. First we are going to run the one stage. Let's say this one is a stage one. Then the stage one output will be given as an input to the stage two. Then the stage two output will be given as an input to the stage three. Then stage three output is going to be the final output actually. So you see, it's not something only one stage that you are going to run and you see the final one. When you process the stage one, you see that output, right? So that output will be stored in a local file system, non-DFS. And once your stage two, I mean started, that will be given as an input to this one. Then your stage two output will be stored in a non-DFS actually. Then once that is done, your stage three, this will go to the final output will go to the HDFS. But the stage one and stage two output is a temporary output actually, intermediate data, which means once you see the final output, you don't need this temp one, stage one and stage two output actually. So this is called intermediate data actually. So in order to hold your intermediate data, temporary data, we are going to utilize this local file system. But of course, once you are done with your map reduce, this temporary data will be deleted. It will be deleted. It will be cleared off from the space actually. Okay. So that is what the DFS and non-DFS actually. So any questions so far? So now so far, whenever you place any file here, that will not be divided, friends. Non-DFS, it's just a local file system, but this will be used only to store the temporary data on the fly whenever you're running the MapReduce program. We will see in depth about at the time of MapReduce, but other than this one, to store your configuration files, if you want to install anything in this one, if you want to copy the data from outside world into the Hadoop world, initially what we do, we cannot just directly dump into your Hadoop world, because it's not a safe data, it's not a good data. We have to validate that first. So to do that validation, initially we are going to do a thorough check by copying the data into the local file system. We see any malicious things are there, good bad things are there. Once that is done, you're going to copy into the HDFS file system. So these are the different purposes having your non-DFS actually. Okay, so these are all about the homogeneous, which means same configuration they are going to follow. For example, each and every machine is having the different configuration. For example, this guy is having 5 terabytes of hard drive. This 5 terabytes of hard drive, right? For example, if I'm going 60% towards the DFS, and remaining 40% I am going with the non-DFS actually. So 60% is the DFS, which means 5 terabytes of 60% will be allocated for the DFS file system, and rest of the things will go for the non-DFS. And here, for example, you're having 2 terabytes of hard drive. 2 terabytes of 60% will go to the DFS, and rest of them will go to the non-DFS. For example, here you're having 16 terabytes of hard drive. Then 16 terabytes of 60% will go here, and rest of them will go to the non-local actually. The same thing here also. For example, here 500 GB only you have. The 500 GB, like how we divided 60% of 500 GB will go towards your DFS, and rest of them will go to the local. So you see, more DFS means, what does that mean? More blocks you can accept actually. So in fact, if you are keeping this space, and this space and this space, all if you're going to keep together, these are the place that you're going to get it actually. Your DFS will come contribution of each and every machine actually. If you're having more space means more blocks you are going to accept from my name node actually. If you are having less space means less blocks are going to be accepted by the name node actually. Very simple concept. So these particulars, whatever the data node level, how much is a DFS and non-DFS, how many blocks are accommodating, how much is a leftover space, how much is the remaining non-DFS space, and everything we are going to see individual at the data node level. And when you're going to keep all this information together, you're going to see at the cluster level all together actually. Okay, so that's how it's going to work out. So that's almost we are done with our theory. So tomorrow I will start with the hands-on. Let's start with the hands-on with our tomorrow's discussion. Okay, so any questions from anyone?
Shiva, please can you repeat what is the content of the BR or the block report?
Yeah, so BR is nothing but a block report. A block report, nothing is a new concept. So here, for example, if you are taking the data node 2, data node 2 is accommodating, for example, 5 files blocks, right? 5 files, probably around 100 blocks are there. I mean, portion of the data has been accommodated by the data node 2. So this 100 blocks information will be stored in this metadata. That metadata information will be shared with the name node every 3 seconds, so that your name node is going to make sure is metadata is up to date, right? That is what block report, which means your blocks are accommodated by which data node is going to be captured by this block report actually. So yes, I am there with data node 2, and this is what the information, and this is what sometimes you see you on your computer, your file will be active, but the data whatever it is there in that, it is not be junk data. You may not able to process it, right? So those kind of information is going to be just carried from the data node to the name node, and the name node is the one who is going to capture the information and keep it in the metadata actually.
Okay, Shiva, thank you.
Yeah. So any other questions from anyone?
Hi, Shiva.
Yes, Surendra, go ahead.
So, is it the blocks which are going to report to the name node, or is it the data node which is going to the report name node?
I mean, both. Data node has to report. Along with that, your block information will be carried actually.
So all the blocks information will be carried in one single ping, right? For every 3 seconds means the data node is going to
Yes,
report to the name node.
correct.
Okay. Thank you.
Yeah, good. Any other questions before you end up? Good. So that's all I have for today. Thank you so much, and we'll meet again tomorrow. Thank you.
Thank you, Shiva. Good day.
Thank you. Bye.
Thank you, Shiva.